Alrighty, let's see. Today is supposed to be talking about cascaded op-amp circuits. So do any of you guys have any questions regarding that topic?
Was that the video lecture 6 thing?
It should have been. Let me double check that real quick. Let's see.
Ah, yes, here it is. I found it.
Yeah, so in a cascaded op-amp circuit, that's simply a circuit where multiple operational amplifiers are chained together to perform a specific task. So unless anybody has any specific questions on that, I'd like to talk about, I think, one of the homework problems.
Sounds good to me.
Yeah, the analysis of them, I believe, is fairly straightforward in as much as you can approach them in the method that we have been doing by figuring out what the voltage is at the non-inverting terminal, transferring that voltage over to the inverting terminal, and then effectively performing nodal analysis at the inverting input node of each amplifier, which is very similar to what we did in the circuit that we worked yesterday with multiple op amps. So I want to take a look at this design problem. Problem number 5 on homework set number 5. So let me see if I can pull that up real quick. Let's share the screen. The last page. Alrighty, so problem 5 asks you to design a multi-stage or cascaded op-amp network that takes an input signal Vn of t is equal to 5 cosine 120 pi t and outputs a voltage signal of 2.5 volts plus 2.5 sine 120 pi t volts. All resistor values used must have a value of at least 1 kilo ohm, and then you're asked to verify that your design behaves using LT spice. So that's pretty boilerplate there. So you're asked to design a cascaded op-amp model. So I'd like to talk you guys through and get your input on how you think the design process for something like this should go. So let's first look at our input signal and our output signal, right? So we're going to talk our way through the stages at a minimum that we're going to need, right? So our input signal is over here, 5 cosine 120 pi t. And then our output signal is going to be over here, 2.5 plus 2.5 sine 120 pi t. So my question for you guys this morning is, how do we get from the signal we have on the left-hand side to the signal we get on the right-hand side?
Freaking magic.
Magic. Okay, well, that's a circuits 1 answer. We're in circuits 2. We're going to think about things practically. So While it does seem that maybe op amps work by magic, it's not the case. They follow some very specific rules, and that's going to make our job a little bit easier. All right, so let's look at this bit right here. On our input signal, we have a cosine function, and on our output signal, we have a sine function. So cosine and sine are 90 degrees out of phase. You may recall from your Circuits 1 sinusoidal signal review lecture. That would have been like the first part of lecture 19, I think. So how are we going to introduce a 90-degree phase shift? Let's start there.
It's a sine of whatever plus or minus 90, right?
Yeah, I don't recall off the top of my head whether cosine is sine plus 90 or minus 90, but yeah. So let's break this down a little bit further. What mathematical operation could I do to a cosine function to generate a sine function?
Could you take the tangent of it?
So the tangent of a cosine function. Not sure what that's going to do. Not sure how I would take the tangent with an op amp either.
Dr. Hartman, would you use like one of the different integrating amplifiers or to go from that? Is that what you're referring to?
Yes, absolutely. So you could use either a differentiating amplifier, because if I'm not mistaken, the derivative of cosine is negative sine, or you could use an integrating amplifier, because I believe the integral of the cosine function is a sine function. So either one of those is a valid option. So our first stage amplifier circuit, I'm going to choose to use a differentiator. The reason that I'm going to use a differentiator is because the integrators, the integration operation for in circuits usually has some sort of initial condition that I need to pay attention to, and I don't want to have to deal with that because that would effectively require me adding also a switching circuit, which is going to be potentially annoying to implement. So my first stage is going to be a differentiator. All right, and so this signal here then is going to be the time derivative of Vn of t. And that differentiator is also going to have some scaling that goes along with it, right? Because the derivative of 5 cosine 120 pi t is going to be, let's see, negative 5 times 120 pi t. Or excuse me, negative 5 times 125 times sine 120 pi t. So there's going to be an omega in there as well, and hopefully you guys remembered from how the differentiator circuit itself works. There's going to be a factor of a 1 over RC thrown into the mix as well, right?
Yes, sir.
Yeah, so the differentiator circuit adds a scaling factor of, if you use the capacitor-based one, adds a scaling factor of 1 over RC. So that's where our component selection is going to come into play, right? So we know that this magnitude of 5 needs to be reduced to a magnitude of 2.5. So that's where our actual component values come in. All right, so we have effectively at this point at least figured out some means by which to convert the cosine signal into a sine signal. How are we going to introduce a DC offset? So effectively, what are we going to do to put that 2.5 volt signal into our output?
That'd be a non-inverting amplifier.
So what a non-inverting amplifier does is it makes the signal larger. So if we feed a sinusoidal signal into a non-inverting amplifier, we're just going to get a larger sinusoidal signal. So what mathematical operation is occurring right here?
Addition.
Okay, so what kind of amplifier circuits can we use to add signals?
Breaking summing amplifiers.
Sure, we could use a summing amplifier, or we could use a differencing amplifier and subtract a negative signal. Probably a summing amplifier would be better here. So what I'm trying to impress upon you guys is that operational amplifiers, by definition, are used to perform mathematical operations on signals, okay? That was their role when they were developed at the beginning of World War II. It's still what they're used for today. Signal processing is all about just performing math on a voltage signal as opposed to, so a continuous stream of numbers as opposed to discrete numbers like the digital operations that you would see in a typical computer. So to do a design problem like this is really just figuring out, all right, so what steps do I need to do the math in, and then what op amps do I need to chain together to do those individual mathematical steps. So we've seen that we need to do a derivative in order to get our cosine signal to a sine signal, and then we're going to need to do some sort of addition. Oops. Summing amplifier here, and this is going to give us the derivative, and I'm going to put a scaling factor of k here plus DC voltage. So this is what our signal is going to look like at our output. So our two stages are, oops, a differentiating amplifier and a summing amplifier, and I'm going to leave it up to you guys to figure out what your component values and all that kind of stuff are going to be. So I'm going to create another effective example problem, design problem real quick that would require the use of a cascading amplifier scheme. So let's say that we are trying to create a way station. So we're going to have four, I'm going to write this as LC for load cells. And the idea here is that you would park a vehicle on top of these four load cells and then add together the resultant signal to look at the weight. And let's say that each load cell generates 1 millivolt for every 1 kilogram of weight on it. All right. We want to design a system that outputs the weight in, let's say, metric tons. On a multimeter. How could we approach this, I hope, fairly simple design problem? Any ideas? This is our car. That's a load cell. That's a load cell. And then there's going to be another associated load cell for each of the other 2 tires. That's a crappy looking car, but I hope you get the point of it. All right, so let's think about our system, okay? We want to know what the total weight of the vehicle sitting on top of the load cells is. So what are we going to have to do to the individual signals from each load cell?
Gonna have to add them together.
We're going to have to add them together. Okay, so that's step 1. So we know that our initial signals are going to have to go into some sort of summing amplifier. Now, are any of these signals going to need to have a different scaling factor associated with them? Or do we want all of the load cells to contribute equally?
I think you should want all of them to contribute equally.
Yeah, they're all going to contribute equally. So we need to make sure that we're not using a weighted summing amplifier, right? Because that's an option. We can choose the resistor values to where we can scale the weight of individual load cells, or we could do it to where we all of them are contributed equally. So let's look at an op-amp configuration for this guy. Let's see. So for load cell 1, we're going to have some value VN1. We'll call it uptime, even though it's likely going to be a DC signal. So here's all of our signals, our input signals. So a summing amplifier, we have 2 options here, okay? The first option is a inverting summing amplifier, and the second option is a non-inverting summing amplifier. So let's go down here a little bit, or actually let's go to the next page. So for an inverting summing amplifier, oh, I need to add another thing. Edit, document. All right, so an inverting summing amplifier. Oh my gosh, my dogs are going nuts because somebody's honking their horn outside of my house. So an inverting summing amplifier is going to look something, oops, like this. We have negative feedback path. So let's call this RF, V out. And we'll just do it for 3 signals, but it should be pretty easy to see that we could do it for effectively an infinite number of signals in a moment. And let's call all of these just R. So if we apply our ideal op-amp rules, no voltage drop here, no current here or here, should be pretty easy to see that the voltage present at our non-inverting terminal is 0 volts, which means the voltage present at our inverting terminal is also 0 volts. So we're going to have some current flowing through this resistor, some current flowing through this resistor, some current flowing through this resistor, and then some other current flowing through our feedback resistor. Let's call this I1, I2, I3, and IF. And applying Kirchhoff's current law, we can see that I1 plus I2 plus I3 is equal to IF, where I1 is V1 divided by R, I2 is V2 divided by R, I3 is V3 divided by R, and IF is negative V out divided by RF. From this, we get V out is equal to negative RF over R1 multiplied by the sum of V1 plus V2 plus V3. So that's how a inverting summing amplifier works. Fairly straightforward. A non-inverting summing amplifier is significantly more difficult to employ. Like it's very straightforward for 2 signals, but every signal after that becomes more and more cumbersome to use. So I'm going to suggest that we use this guy for our first stage in order to simplify the amount of math in the design that we're going to have to do. So to that end, all right, minus, plus. Okay, so now let's talk about our component values. Our load cells generate 1 millivolt for every 1 kilogram of weight, right? That's what it says literally right here. So we want the output of our system to display the weight in metric tons. This might actually be too easy. The reason why I say that, it won't be that bad. All right, so we get 1 millivolt for every 1 kilogram of weight, and we want to display the output in metric tons. So how many of you know how many kilograms are in a metric ton?
No idea.
Give it a Google.
All right.
One of you. I'm surprised none of you know this.
Oh, is it just 1,000?
Yes.
Wow. Okay.
Yeah, so that's why I'm surprised none of you like it. Anyway, so if we want our output signal to be expressed in metric tons, then what kind of scaling are we going to have? So effectively, 1 metric ton should be equal to 1 volt. That's the constraint I'm going to have. So if my multimeter reads 3.87 volts, it means that this vehicle weighs 3.87 metric tons or whatever. So how am I going to appropriately size my resistors? Do I need to have some sort of scaling factor in there? For instance, let's say that on this input here, VN1, I have a weight of 800 kilograms, which means my voltage signal should be 800 millivolts, right? Yes or no? Okay.
Yes, sir.
And let's say on VN2, I have somehow only 400 kilograms. Maybe the people that are in the car have distributed the weight inside very poorly. So this should be 400 millivolts. And let's say these guys are 0 and 0 just to make our math easy for now. All right. So we have a total of 1,200 kilograms. So our output signal should be 1.2 volts, because that would be 1.2 metric tons, right?
Yes,
Correct.
sir.
Okay. So how am I going to choose my resistor values to make this happen?
They
So how this
shouldn't.
guy is supposed to work, just to be clear here, is that our output voltage should be negative RF over RN times V1 plus V2 plus V3 plus V4 if all of these R's right here are identical.
So then should RF and RN be the same?
Yeah, there should just be a simple 1-to-1 ratio. So we could put 1 kilo ohm here, 1 kilo ohm here, 1 kilo ohm here, etc., etc. Right? Simple 1-to-1 ratio. Then the only problem that we would have would be that our output signal is negative. So how would we fix that?
Could
Could
you
you
measure the
just-
input voltage negative?
Sorry, 2 people were talking and I heard something about just negative.
Go ahead, Dan.
Oh, I was gonna say, could you just use another op amp,
Yes. So what kind of op amp would we use?
an inverter?
Okay, so we'll use an inverting op amp. So we'll feed the output of our summing amplifier into an inverting op amp. So there is our resistor. here's our output voltage for the system. So what resistor value should I use for the inverting op amp? Where I have another feedback resistor, let's call it R2. This resistor right here is R1. So what's the relationship have to be for those guys?
They should also be the same.
Right, because we want to gain an overall gain of 1. We don't want to mess with anything. So we could put these as 1 kilo ohm and 1 kilo ohm as well. So nothing crazy there. Okay. What if we wanted to change the output from metric tons to, that was not what I was expecting it to happen, but an imperial ton. Yeah. Where what I mean by an imperial ton is 2,000 pounds is 1 ton.
The conversion factor for that is fairly close, but it's a little bit less than metric tons.
Right, so there is 2.2 pounds in 1 kilogram. I believe. Let's see, there's 1.6 kilometers per mile, 454.56 grams per pound. So yeah, 2.2 pounds is 1 kilogram. So how are we going to convert it? Let's not worry about the figuring out the exact mathematical relationship. That'll not necessarily waste time, but you guys are engineering students. You should be able to figure it out fairly quickly. Where in our scheme can we make that change? Let's say that. So how would we go about implementing this different conversion factor?
That would just be scaling it. Would it be easier to do it on the inverting amplifier because there's 2 resistors there?
Yeah, so that would be probably the easiest bit. So we would just simply add all of our voltage signals together in a 1-to-1 ratio on the summing side, because in my mind, that's going to be the least confusing way to do it. And then we can apply our scaling factor here on our inverter, where we're flipping the voltage signal from negative to positive, and then we're going to scale it to give us the correct output. That seems perfectly reasonable, and it's less work. Or it's less, less components, so it's going to be easier to implement as well. So that's a fantastic place to do it. Now we've effectively covered 2 design problems using cascaded op amps. So are you guys kind of seeing like how cascaded op amps are used? We're just, for a particular design, it's literally just figuring out what kind of mathematical steps we need, and then which amplifiers we have to chain together to get those mathematical steps in the right order. It's literally that simple.
Yeah, this actually helped quite a lot.
Great. Anybody else have any questions, comments, etc. on this stuff? The analysis-wise, it's the exact same thing that we've been doing. It's just now there's more op amps in a row. So I don't want to beat anything to death because we've been covering this stuff for a week now. But as far as implementing multi-stages, this is just kind of how it's done. You just string them together to get whatever output you want. All right, excuse me. Any other questions on homework assignments or this material or anything?
Yeah, I have a few for homework 4.
Homework 4. All right, let's see. File, open. 223. All right, Devin, what are your questions in regard?
So I guess it's more of a general question. For problem 1, for my RN value, I'm getting a massive resistance. Should I rework it or?
Let's find out. Second.
I just figured I'd ask because the example you did in the lecture, it came out to only be like 5 kilo ohms.
Right, but that was for a, so this is a non-inverting amplifier, and that was for an inverting amplifier.
Yeah,
So,
like this seems like it makes sense because the only place the current can flow is actually into the op amp, but I'm just not sure.
yeah, let's find out. Just a second, I'm trying to copy the image over. Copy. Let's go ahead and throw another page on here. All right, so we're using the practical op-amp model. So that means we're going to have something that looks like, that finger's out of the way. Oh, I have the wrong thing selected, that's why. All right, I'm going to make this my inverting, this my non-inverting, so that this is VD. The reason I do that is because it's going to let me do my feedback loop a little bit easier. So let's see, so my feedback is going to be 3 kilo ohms. This is R out. I do have a load resistor of 8 kilo ohms that I'm going to have to pay attention to. I have a 1 kilo ohm resistor from my inverting terminal to ground. Wait, that's a bad way to put that. All right, let's see. So from this is my 5 kilo ohm resistor. This is my 2.5 volt source. And then this is my 1 kilo ohm resistor. Let me double check that I've drawn this correctly. This is ground. All right, so between the inverting input terminal and ground, I should have a 1 kilo ohm resistor. That's this guy right here. Between the non-inverting input terminal and ground, I should have a 5 kilo ohm resistor in series with a 2.5 volt source. I should have a 3 kilo ohm resistor between the inverting input terminal and the output terminal, which is right here. between the output terminal and ground, I have an 8 kilo ohm resistor, which I have drawn that. So really, I just need to know what RN, ROut, and AV are. What's RN from the problem statement? Anybody know that off the top of their head?
It is 150 kilo ohms.
ROut
Is 250.
ohms.
Yep.
And AV is what?
4,200 volts per volt.
All right, so it's 4,200, where VD is always V plus minus V minus. All right, so if I am not mistaken, we're looking for, the question that you have is with regards to the input resistance, right?
Yeah.
And the little r in. So the input resistance seen by the 2.5 volt source, which is going to be that 2.5 volts divided by whatever this current, I'm going to call it I in is. All right, so that's going to be, get out of the way, back fingers. Two 0.5 volts minus whatever V plus is in a minute, divided by 5 kilo ohms. All right. Okay. So to analyze this guy, we're going to have to do nodal analysis at the non-inverting input terminal, the inverting input terminal, and the output terminal. So KCL at the non-inverting input. So that means we are going to want, let me change the color so I don't confuse myself. This current and this current. So that's going to be V plus minus 2.5 volts divided by 5 kilo ohms plus V plus minus V minus. Dang it. Turned on Microsoft Store for some reason. Over our input resistance, which you said was 150 kilo ohms. Zero. We're going to have to do KCL at our inverting input. So that is going to be this current, and this current. So it's going to be V minus over 1 kilo ohm plus V minus minus V plus over 150 kilo ohms plus V minus minus V out divided by 3 kilo ohms equal to 0. And lastly, we're going to have to do KCL at our output terminal, which is going to be this current, and this current added together. So we're going to have V out minus V minus over feedback resistor 3 kilo ohms. Double check that. Yep. Plus V out minus 4,200 V plus minus V minus divided by R out, which was 250 ohms plus V out divided by 8 kiloohms is equal to 0. So those are our three equations. Give me just a moment. Pull up MathCAD. All right, so I'm going to have a solve block. All right, so I got, oh crap. The plus is 2.5 volts. The minus is 2.497 volts. And the out is 9.989 volts. So from this, I need to make this.
Yeah, because I got it's like 2.4999.
Yeah, let me put more significant figures there. Because yeah, right now, effectively, it's saying the input resistance is infinite. Yeah, 2.4999, blah, blah, blah. Okay, so IN should be 2.5 minus the 5 by 5. 144.156 megatons is what I got.
Yep, that's exactly what I got.
Okay, then that seems legit. And it's vastly different because it's a non-inverting amplifier versus an inverting amplifier. Yeah. So.
Yeah, so the reason it was 5K in the example you did was because the current could flow around the op amp.
Effectively, yes. And here we're forcing it to all flow into the input terminal.
All right. I was just a bit confused. Thank you.
Yep. Nope, no problem. All right, so let's look at other homework for, where did I open up? Maybe I opened it up in here, sorry. Yeah, I did, I just couldn't see it. All right, so you said you had other problems potentially about homework 4?
Problem 2 as well. I solved it. I'm just not sure. Could you verify this in LT Spice? Like, I'm not asking you to, but is it possible? Because I tried it, and it's like the values were close, but I don't think it was using the ideal op amp.
So to make LT Spice, you use the ideal op amp rules. Just change the spice level to 1.
In the like the op amp menu.
Yeah, so when you right click on the op amp in LT Spice, it should say something like spice level 2. To make it an ideal op amp, change it to spice level 1.
All right. And you mentioned something in the most recent lecture that you can't do Kirchhoff's current law at the output node. Would that apply here, or is that like not relevant to this?
So you can't do Kirchhoff's current law at the output node. So the reason that I was saying that is because we don't have a relationship for the output current IOP. Like, I'm trying to think of the best way to put this. We couldn't do KCL at the output node to solve for other nodal voltages and stuff like that, because we don't know what the contribution of this output current is going to be. For this problem, we're trying to find the contribution of that output current, which has to be this current flowing up through the 500 kilo ohm resistor and this current flowing down. So once we know what all of our nodal voltages are, then we can figure it out. But we can't use this output current to figure out what our nodal voltages are.
Okay, that makes sense.
I think any. Yeah, so we can't use this guy to find this voltage or this voltage, etc. But once we know those voltages, then we can use those voltages to find that current.
All right.
The issue is that there's not a mathematical relationship between those voltages and current. So like we know the output current is going to be the sum of those currents through the resistors, because Kirchhoff's current law must be satisfied. Not satisfying it is literally a violation of the laws of physics.
All right, that makes sense. I just need a clarification.
Okay. Any other questions?
Not for me, but in the future, because I emailed you yesterday.
Yeah, I put a little, I put it in red to remember to remind myself to respond to you, but I didn't have a chance to do it.
All right, I was just wondering if you got it,
Yeah,
or if I've been emailing the wrong person or something.
So you've definitely been emailing me. And generally speaking, I would actually, like, I don't mind answering the emails and all that kind of good stuff. It slipped my mind yesterday. But this class time is a perfect place to ask those questions as well, because you might be the only person with, let's see, the courage to ask the question, but it's going to help other people to see me work through these things too. You know what I mean?
Yeah. So I'll just save them for class then.
I mean, you don't have to by any stretch. And if your homework's due soon and something arose at the last minute, by all means, email me and I'll try to get to it. But class is a perfectly acceptable place to ask those questions as well.
All right.
All right.
Well,
any questions
from me?
anyone else?
I've got one on problem 3.
Problem 3. All right, Gord.
Um, I think I set it up correctly and I got an answer for it, but I just wanted to see if there's uh like if there's a correct way to set it up or if I did it incorrectly. So if you don't mind, could you set that up? Just I can have to do anything. I just want to see if I did it correctly.
All right, so how I would set this guy up, let's see. Gonna identify my nodes because I might run into an issue here. So this is all my ground node. This is my inverting input terminal, so my nodal voltage there is going to be V minus. This is my non-inverting terminal, so this voltage is going to be V plus. And because this is an ideal op-amp circuit, those voltages have to match, just to be super clear about that. Then we have, this guy here. Let's call it node A, just for the sake of argument. And then here's my output voltage node. All right, so let me take a look at this real quick because it's been a hot minute since I did this one, and I think the solution to it is in my office at Tech. All right, so I believe, as per usual, my first step should be figuring out what the voltage V plus is. So V plus is the voltage drop at the non-inverting terminal with respect to ground. So that means it's actually just this voltage over the 3 kilo ohm resistor. Can you understand why that's true?
Yes, sir.
Yeah, so it's the potential difference between this point, which is the light blue node, and ground, which is the orange node. So V plus is going to be 4 volts times 3 kilo ohms over 7 kilo ohms. That's just using voltage division, so that's 12 sevenths of a volt. Then, if I apply KCL at the inverting input node, I'm going to have V minus over 1 kilo ohm plus V minus minus 4 volts over 2 kilo ohms plus, I'm running out of room here, V minus minus V out over 5 kilo ohms is equal to 0. And I know that V minus is equal to V plus, so I have one equation, one unknown, and I could solve for V out. So that's how I would set it up.
Awesome. Thank you.
Any other questions? Problem 4 is derivation problem. Should be extraordinarily similar to what was in the video lecture there, so that should be easy enough-ish. And then problem 5 we've already talked about. All right, unless anybody has anything else to talk about today, I will catch you guys on Thursday, where we're going to start talking about something brand new. believe.
Roger that. Thank you, sir.
Yep, you guys have a good day.
Thank you.